Right, welcome everyone to Neuroccino on this Monday morning, 9:30. I think we have 3, if not 4 papers today, depending on people show up. I think it's a holiday today in Italy, isn't it? Yeah. Well, thanks for coming, guys.
Tomorrow is a holiday, so a lot of people today not working.
Great Italian established that. I'm in the wrong country at the moment. Right, let's get started. I think Leah and Victor, you both have a paper for us today. How about you start us off, Victor?
Yeah, sure. So here, right. So is Michel here?
I can't see him yet, but he's supposed to come.
Yeah, he had a paper, I think, last week already.
Yeah, I was going to give him first place, given that I pushed him to this week. But
yeah.
First come, first serve.
Yeah, sure. All right. So, do you see it well? It's okay?
Perfect.
Perfect. Thank you. So this paper was published in Nature Methods, I think 2 weeks ago. It's a paper about the simultaneous recording of the brain activity through both calcium imaging and fMRI imaging. So this is something that has been done before on the principle, but never with such a wide field view in the calcium imaging. So it's really neat. With the concurrent optical setup that they have. So what they do is, so it's in mice. I have to say it's not in human because, well, I mean, calcium imaging in human, I don't know if it has been done. I don't think so. So they use transgenic mice that that express the calcium indicator in excitatory neurons. So it's specific to excitatory neurons. So it's a caveat, but it's more a proof, since it's a method paper, it's more a proof of concept than anything, but it works really well. So even with only excitatory neurons. So with the setup, it's so an 11.7 Tesla coil. So it's a very powerful fMRI. And they to do the optical imaging, what they did was well, do the classical skull thinning of the mice, and to put a cranial window on top of it. And then they use a camera that is with an array of 1,000 optical fibers to get to the actual to get inside of the machine, so that there is no metal parts inside of the machine. So this is the technical part of it. So basically a remote camera using optic fibers with a quite a neat, quite a good resolution, 1,000 pixel by 1,000 pixel over 1.4 centimeter square. And for so they could record both of the signal at the same time, and they registered the data using the veins and the arteries in the brain. So they are visible on top of the brain with the optical method, and they did an angiogram using an fMRI method to get it inside the MRI sequence, and it gets them something that it allows them to align both imaging very well. So it's a good method for this. And so they tested different type of of recordings. So one with Hindper stimulation, like electric stimulation, to have some kind of classical activation task here, but task sort of. And as you can see, it gives results like very similar in both bold and calcium imaging. So it works well. And what they did also was to create a transfer function from the calcium imaging signal to the bold fMRI signal to try to predict using the calcium imaging how the bold signal will look like, so that they can say, okay, if we can extract this information from the calcium imaging and predict the bold imaging, it means that they are really linked together, and they are really the not the same, but the bold imaging is well represented. So they managed to doing that. So it's a bit messy, but we can see here on this graph that they managed to do it. I think it was during a resting state. They did this on resting state. I'm not sure. And so in orange you can see the bold signal for a region, and in green the calcium imaging, and in blue the prediction of the bold signal using the calcium imaging through a transfer function. Well, problem is the blue and the green are quite similar in color, so it's hard to say. But in the results with their transfer function, they managed to explain 30% of the variation of the bold signal using only a calcium calcium imaging signal. So it's quite good. It's quite good. Also, it depends also on the frequency band that they use in the bold signal, because they did some they filtered temporarily the signal. That is something that we usually do in a resting state analysis. We only keep the low frequency band of the bold signal, the fMRI signal, and here they showed that it works well. It works the best in this low frequency band, and not as well in the high frequency bands of the fMRI. So they discussed this, but here, since it's just a methodological paper, I just wanted to show you quickly the results and say they also tried some automatic segmentation of the brain with the some data-driven method, and show that they got some quite similar results when comparing the parcellation of the brain using calcium imaging and the one using the fMRI imaging. So this is another way to conclude that they have like results that are similar in both ways. And well, that they did some other experiment, but that's the core of the paper. And this in the end, this is a very good big step forward in this kind of concurrent imaging to understand better the bold signal, which is a very indirect way to get to the neural information, because it's a hemodynamic signal, and it's not super well understood. Well, it's getting better. We are getting better at understanding what is exactly happening with the bold signal, but it's still a work in progress. And this is a good paper to show what we can do to better understand it. And it's really good because it really show in the global, well, in a very wide field view, the spatial relationship between the calcium signal, so really almost instantaneous signal, with the very indirect signal of the fMRI bold signal. Thank you.
Thank you, Victor. How long do you think it would take to upscale this to the human brain?
Thing is, I don't think it's possible at all because of the intrinsic problem with the calcium imaging stuff, because you have to have transgenic neurons that I don't think we will do that in human. But in apes, that would be another solution. I don't know if there are models of transgenic model of apes with calcium indicator in the brain for these kind of animals. Thing is, it's in principle they say that it can be upscaled without a problem, but it must be probably hard. Also, one problem is that we can only image like the here the top of the brain, only the tissue that are available and close to the skull. But in theory, if efforts were made to get there, in a few years we could have something on a way greater scale. But I don't know if there will be effort in this direction.
Thank you. Are there any questions? I can see Michel. Yes, go for it.
Thank you, Victor. It's great. Why is imaging calcium so interesting?
Calcium specifically, well, it's, as I understand it, it's a way to get to the to when the neurons are firing, since it's the molecule that the neurons use to signal that the neuron is supposed to fire with or to release the different neurotransmitters. So this is a way to get to the almost instantaneous activity of the cell. Also, although it's true that it's not like the electrical activity like we have when we do measures with electrodes, but it's still a way better temporally way to know the firing of neurons than fMRI. Here they do 20 frames per second, which is much higher than what we have in fMRI. Because the fMRI, for example, it was a TR of 1 second, so 1 frame per second. And so we have a much better temporal resolution with calcium imaging.
I'm saying that because so they don't mention glial cells in the paper.
No, not here. That's true. But also they say that it was just a model of one type of neuron and one type of cell. And since it's modification through a genetic modification, you could target any kind of cell population that you want. They just used here for an example. So
because like the glial cells, which are like way more numerous than neurons in the brain. I think it's about 10 times more. They communicate with wave of calcium.
awesome.
When I saw the title, I was like, "Oh my God, this is happening!" But they didn't mention it. So I wonder whether this is possible too.
But I'm sure it is, and it's I think it's very interesting too, because also I think there is a relationship of the activity of glia cells with the bold fMRI too.
Right. So there is always an activation of glial cell when a neuron activates, but there's not necessarily an activation of the neuron when the glial cell activates.
Yeah. So yeah,
the glial cell has a bold signature.
So yes, I think it would be a good follow-up, but I didn't see any mention of glial cells. They did say that it was only the excitatory cells, so it was very limited and could be broadened later. But yeah, that's a good idea, I think.
Thank you both. I like your optimism, Victor. Of course it can be done.
Always, always.
I know, love it. Right, are there any other questions? Can't see any raised hands. In that case, we move on to the next paper. Michel, thanks for joining us. I pushed you to this week, so go ahead, present your paper.
I lost the paper. I had it in my background, and I don't know where it is. Oh, I have it. I have it.
Okay.
Just gotta share the right screen. I cannot share my full screen for some reason.
Share your PDF.
Can you just now? Can you just make? Yeah, there you go. I'm gonna share this. For some reasons, they made an update and I cannot share my full screen, and I cannot share the page where I have. All right, I get it. I get it.
That's what happens when you come to professor level.
You suddenly become an idiot. Can you see toward
Did not say that.
Do you see toward linking diffusion MRI based macro and microstructure measures?
I see a white page. And a lot of people nodding.
How about now?
Yes.
All right, cool. Sorry for the delay and not being super ready. This paper came out last week from the team of Damian Wasserman. And so what they tried to do, they followed up patients with brain tumors that were having a neurosurgery, and during the neurosurgery, the neurosurgeon used electrocorticography, which is like they put a grid onto the brain and they can record directly from the brain of the patient with the skull open, like kind of the activity, what's going on there. And by doing so, they were able to look at the relationship between a stimulation and the apparition of an N1, which is a typical wave that you can have distant from the electrical stimulation that the neurosurgeon is applying to the cortex, and an N2 measure, which is another wave that you can see also that is a reaction to the stimulation that the neurosurgeon is doing. So, so the paradigm is you have the patient, skull open, electrocorticography onto the brain directly, and the neurosurgeon is stimulating, and on the electrode, stimulating electrically, and on the electrode on the surface of the brain, you record response to this stimulation, which is the N1 or the N2, and we calculate the time that it takes between the stimulation and the apparition of the N1. That gives the team of Damian Wasserman lag that is different according to the electrode that you have onto the surface of the brain. And so what he tried to do, he tried to see whether tractography, individual tractography or reconstruction of the fibers in the brain of these patients in terms of microstructure, which is like basically a number of streamlines and their length, and microstructure, which is a fractional anisotropy or any other kind of measurements that you can derive from the behavior of water. They try to see whether they can predict the lag between the stimulation and the N1 and the N2. And so this is a typical grid that you have. See, they have like several electrodes onto the brain, and they calculate for the arcuate fasciculus whether the way your brain is connected in number of streamlines and the lengths to travel, whether this can predict the lag in N1 and N2. That's how they did the tractography. And then what they tried to do, as I said, is to predict the lag, which is coming toward the end right here. And you can see that you can. And that's, so that's linear regression, where you combine the measure of distance and number of streamlines. you can see that you can predict, and you have like a cloud that is elongated that shows that your prediction is actually not bad at all for the lag in terms of N1, which would be directly the electrical communication along the wires. It works for the microstructure only. It works for the macro and microstructure together. It's actually a little better. And this, in the abstract, they say can explain, so they have a correlation of 0.5 and 0.47, which means that they can explain the delay and the amplitude of the N1 with 25% of the variance of the delay and the amplitude can be explained by those tractography measurements, which is really, really, really good. And this can also predict like the location where it happens with a high specificity and sensitivity, which is important in terms of clinic and the way, you know, neurosurgeon can kind of build the planning of the surgery. Another information that I found in the text, and I thought was important to mention, they speak about quite recent paper that came out in Nature Communications, speaking about false positives. There you go. All right. I'm just trying to find, I saw it, but maybe that's not the one. No. Yeah. So in the paper published by Meyerheim in 2017, they reported that 36% of streamlines generated by contemporary algorithms may link regions that are not actually connected. And there was an approach which was with, you know, like a simulation of the brain. But with the experiment, they actually found that only 6% of false positive, which are like regions that are connected, are actually not connected, and 4% of false negative connection could be found in the brain when you compare their approach looking at electrometry with tractography. So much lower number, which is very encouraging for tractography. And I thought, you know, we've all been bummed by this paper a little bit. In terms of what tractography could do. And this is very encouraging. I was very happy to see that this is way better. That's about it. I'll be happy to take questions.
Thank you, Michel. Very interesting paper. Are there any questions in the room?
Can I ask?
Sure.
Which kind of tractography did they use? I haven't time to see.
The tractography that they used is a matrix, Donald Tournier probabilistic spherical deconvolution.
And another question: did they find all the correlations with the streamlines, or also like TTI matrix? I saw some FA, MD, but
so as I remember, they either did the microstructure only, or they combined the microstructure with the microstructure to refine the measurement. And I think they're doing that because they can't, you know, it's difficult to just use a microstructure because you don't have the microstructure for the streamlines that you do not reconstruct. I think that's why they did that. Importantly, they also calculated, I forgot to mention that, the effective connectivity, and they can also predict the effective connectivity, but not in terms of, they didn't test the directionality of the fibers. I just had a chat with Damien yesterday about that. I asked him whether in his analysis of effective connectivity, they also try to see whether with the tractography measurement that they have, they can predict the directionality. He didn't try that. But he said that the data are freely available for anybody who would like to try. He's happy to share and also collaborate on that matter. So that was a good suggestion.
Thank you.
I think it would be interesting to also compare other algorithms in response to that paper, for example, to see where the difference is, given that the numbers seem to be much lower than the field thought they were. It'd be interesting to see how that holds against different types of processing. Because especially in the clinic, not everyone has access yet to high resolution tractography data.
Well, importantly, it works when you log your number of streamlines. So it's important to use a log version of your number of streamlines.
And there's a question on the chat from Patryk, and he asked, did they say anything about the N1 evoked potential as a surrogate measure for conduction velocity?
That's a good question, and I'm gonna be honest, electrophysiology is not my thing. But so you get like famous waves, and so you cannot, if you stimulate on one side of the brain several times, and you sum up like all your electrodes with regard to this time of stimulation, what you can see in the other electrodes is a reaction that is of when you average it all, which is a first wave, which would be N1, and a second wave, which is N2. So, they try to look at this distance in terms of time and the amplitude over there and see whether they can predict it, because there is nothing before that they could do. You mean like, do you mean like the depolarization that is over here that they could have modeled? I don't know. That's a good question for the authors, I think.
Hey,
so
sorry, I didn't really catch most of your answer because my video is just stuck, and then
gotta do it again. All right.
left.
So again, so I'm not an expert in electrophysiology, as you may know. This is not my strongest field. But so if you stimulate the cortex and then you record all your electrodes and you do it several times, and for each electrode you average your signal, what you're gonna have this profile of reaction in the brain with the first N1 and a second N2. And so what they're trying to look is how much time does it take between the stimulation and the N1 to appear as a reaction of the brain, which will be due to the conduction along the axons, and see whether tractography can help to predict that. So what do you mean? Why did they use T1? You would have used like the depolarization rather than...
No. I mean, it's basically
rather than the depolarization here, because positive.
No, the latency that they're using, the latency measure, is the same that I was using like in 2017 for a not similar paper, because obviously we did electrophysiological measures not within the skull. But we also used N1 differences between two opposing electrodes to see to what extent callosal fibers or the microstructure in callosal fibers actually explain the difference between these N1 evoked potentials in the left and right hemisphere. So during the time, like one question I got that I couldn't really, for my own sake, could answer satisfying to a certain degree of satisfaction is to what extent the N1 signal is actually a surrogate of conduction velocity. Because we obviously believe that the measures that we are having here, the diffusion measures, capture signal in the white matter, which in turn relates to the speed of processing along the fiber, right? However, the N1 signal is based on a local field potential.
Well, okay.
Right.
So you, in principle, you cannot. So I spoke with electrophysiologists, and we wanted to put electrodes in the brain to catch the signal of white matter. And the problem is like you cannot catch a problem like the signal of white matter unless you get inside the axons, because the myelin is such a good isolant that you cannot get it from even from an electrode that will be next to the axon. At least that's what they told me. So, and that's why, you know, people don't really do it. Now they could have modeled P1. I would like to, you know, if we get into details, maybe P1 didn't work, or I don't have a full picture of paper, of course.
But typically N1 has a bigger history in electrophysiology as being a signal that is that somewhat is related to cognitive abilities. And if you look, for instance, in the visual N1 literature, you will see a lot there, whereas there's relatively few ideas about the P1 in comparison. So I think N1 is the way to go.
That's probably the reason why they use N1 then.
Yeah. I was just curious about if they said anything about it.
I just, you know, I wish I knew more about electrophysiology, but yeah, you gotta choose your
niche. You can't know everything.
I can't know everything. I knew about the calcium.
Okay, thanks.
All right, thank you.
Right. Any other questions before we move on? No. Okay. In that case, we have one more paper. Leah, are you ready?
Yes.
Lovely. Over to you.
Okay, yes, the right PDF.
Michel, can you stop sharing, please? Thank you.
Okay, now can you see the screen, right? So this is a recent review about diffusion MRI. I don't know the date because online is published, in the journal is published on the 1st of January, but it's already available. And the title is The Sensitivity of Diffusion MRI to Microstructural Properties and Experimental Factors, because the authors divided the paper in different sections. Starting from like an introduction of how complex is the microstructure, going to the acquisition, the different acquisition that you can have. Then they explain the different models that you can apply to like quantify, have quantitative measures of microstructures. They talk about validations in the end, and the limitations, also some noise problem that you can have in diffusion MRI. So there is quite a wide overview of from a technical point of view. So it's not really focusing on tractography methods, for example, but it's more on the microstructural properties and experimental factors. So it's a really specific perspective. And I really loved the introduction where you have this description of all the different components, so biological components that you have in the gray matter, in the white matter. You have this nice description of the quantifications. So for example, the length of axon that can go from few millimeters to 1 meter. And all the glial cells descriptions, so that you can have oligodendrocytes, astrocytes, macroglia, and the related functions. So to give you like this idea that what we call microstructure is actually really complex. So we are using some models going from a measure that is about millimeters to microstructure, so going down using models. And I really like the introduction. Then you have the pulse sequences that you use to acquire this information about diffusion. So first, the widely used pulse gradient spin echo, when you have two diffusion gradients and you have radio frequencies that flip the direction of your spins. So here the signal, detonation of the signal, give you an information about the diffusivity. This is the most widely used sequence, but you can play around these gradients. So you can flip these gradients twice, and you have a double diffusion encoding sequences. You can make oscillating gradients. So you can, in this way, you are giving more weight to some diffusion properties, for example, like small compartments or the different pores dimension. So here you are more sensitive to small, the diffusivity in small pores. And you can also change, so why use all these shape of gradients? You can also like use different shapes using oscillating gradients, and to really like play and change the sensitivity of diffusion measures that actually is really sensitive, it's really strong. Here you have, I really like the tables that they made to summarize all these a variety of methods. You have a tables here for the different acquisition models, so the applications, so the sensitivity, why they use these acquisition scheme. For example, here you have more sensitivity to microscopic diffusion anisotropy, compartmental kurtosis. So when you look to the exponential like drop of the signal that give you information of diffusivity, you can go to the the first description, like the mean, to other more you can make like an approximation of this curve, and using, for example, kurtosis. You have also the advantages and disadvantages, and a lot of references if you want to go like in deep in these methods. And then they talk about the models. So once you have acquired your data, you can model the diffusivity also with a lot of models. So I know that it can be like, also for me, sometimes it's scary. So, oh my God, I am studying diffusivity for a long time, but I don't know this method. Yes, there are a lot of methods. And for example, here you have these maps of non-gradient, non-Gaussian diffusivity. And this is a ration time from origin, because here they are using this MAP, is the mean apparent propagator. So here you have a model in the Q space that is a space where you are modeling your the diffusivity according to the B values. So it's a space like created for diffusivity properties, and you can do like some transformation, Fourier transformations, to then go to your spatial space. And here you can see that these maps really like highlight different properties in the gray matter and white matter. You can also have these use this other model called the confinement model, that is they say that is similar in the spirit. They say this in the review to the DTI, but they use like spherical harmonics, I think, to model the diffusion. So you have like again these weighting here that you can see, but also like some noise in the ventricles. And it's also nice, of course, to compare the different models and see which are the differences. You can also have maps using another model that is the power law fit. So here you have the the parameters of this power law fitting, and you can compare that to fractional anisotropy. And then they talk also about multi-compartment models. And so the most famous are the diffusion kurtosis imaging and NODI, the rate orientation dispersion and density images. So actually you are making an upper simplification of the microstructures. So saying that that could be like some isotropic diffusivity and some anisotropic diffusivity, and usually the anisotropy is interaxon and the isotropic is in the external component, so outside the axons. And you can play with these different compartments and try to model these inter and extra compartmental diffusivity. And there are a lot of methods to do that. I didn't, of course, there is an oversimplifications. So they also pointed out that these multi-compartmental models have some limits, but I didn't know and where it was. They say that you can also use deep learning. There was a section somewhere where they say that you can use deep learning to infer, so to analyze the different compartments, and they say that is a really promising approach. But of course, to doing deep learning, you have to you need a training model to, because it's a data-driven approach. So you are like you're using a network, a net convolution to evaluate the kernel. So how your net is working, and so you need a training set. So this is limited. This could be also time consuming. Here again, another table with all the multi-compartmental models that you can use. And also, yes, they made this distinction of volume, because usually you say volume fraction when you talk about multi-compartmental models, but they say that the right term is a signal fraction. And because it's really depend on what you are modeling. Here is the deep learning section where they say that there are few of these methods, and they need this training set, but they are really promising. And also, yes, they talk about the validations. So how you validate this data using Monte Carlo simulations, phantoms, fixed tissue, or in vivo and ex vivo validation. Here, yes, I admitted that I read it really quickly because I jumped like here. This is really interesting. So they talk about the noise that you can have in the diffusion MRI. The noise is due to acoustic noise, physiological noise. So for example, the cardiac and respiratory cycles that can be linked to the diffusion, and the thermal effects that you can have in the hardware in the when like you are measuring, you are using like coils, radio frequency impulse, and these also you have your signal, but you have also like thermal noise due to the electrons. And here you can see that if you go up with your B values, of course your you have more noise and your signal drop down. Here they use the same scale to compare the different B values images, but your signal as a drop down. And the interesting thing is here you have the signal to noise ratio maps, so you can see the distribution of the noise, And one thing that they say that now it's mostly used that you use the parallel imaging, so sense graph algorithms. This means that you have a lot of coils that acquire the signal, and you acquire simultaneously the signal, so from different perspectives, from different coils, and then you merge this signal. And you can do that using different methods. So this is why you can use the sense graph. This really speed up your acquisition. This is the in-plane acceleration, and then you can also work on multi-slice accelerations, so acquiring different slices together, but they don't talk about that. They said, but they pointed out that using parallel imaging, the problem is that your signal has not a uniform distribution, but is biased on the location. And as you can see, and this is the problem, because then when you apply the denoising filters, that could really affect your measure, because you are applying like one filter that is the same for all the voxels, but as you can see, the noise is not the same. It's not uniform, and so this could be a problem. And so yes, here they talk about the parallel acquisition. So the noise has a non-stationary behavior, and so we need to be careful about the noising. And then they talk about, of course, so if you then use the one acquisition scheme technique for diffusion, you can change the diffusion gradients, and here they reported the different articles that they discussed these. So you need to have at least 30 gradient directions, and then you can talk about high angular resolution diffusion imaging, RD. And yes, here there are a lot of details. Here I admit that I read it really quickly. Here they talk about the Tournay paper, where they say that you need 45 gradient directions for a spherical harmonics decomposition of 8 degrees. And there are also some equations that you can use to evaluate the number of gradients that you need for your purpose. And yes, I guess you can see there is a lot of models, schemes, articles to know about that. It's a really wide literature, and I suggest this paper to really disentangle all these different perspectives. And jumping to the conclusions. So we are conscious that there is, so in a diffusion MRI, you are doing an oversimplification of all the biophysics underlying the neural structure. But it's an in vivo measure. It's using MRI. It has a lot of clinical applications, as we have seen in the, for example, in the tumor field. And so it's useful. And they say that the different, we are using, of course, the Stan-Kerlak method for acquisition, diffuser acquisition, but there are other methods, as we have seen, like playing around with the gradient shape, oscillating gradients, number of gradients in diffusivity. You can actually improve the sensitivity, for example, in axon diameter. So diffusivity, so in diffusion weighted images can give you also more information that what we are currently using in our studies. Also about pore size, And we have to be careful about this noise problem, because also when now we are speeding up acquisitions, because it's also, this is a problem also in the clinics. You can have a half an hour of acquisition of diffusion of MRI for a patient, or maybe you can, it depends on how you deal with that. And so there is this problem of non-stationary behavior. And we have to be careful about the nosing. And so as a conclusion for the RD methods, at least 45 gradient directions for a good modeling of spherical harmonics. So how you infer the density fiber orientation distribution. And so that's it. I hope to give you like that. I was able to give you like a full perspective of this paper, because you have a lot of details in it, and all these nice tables where you can, like, if you have a specific question, you can go and see which are the articles relating to that. So it's a really, really nice review, and really comprehensive about all the problems, informations, and opportunities that you can have with diffusion MRI. I can try to ask to your question.
Thank you, Leah. Thanks for presenting that paper. That certainly serves as a good reference for the field. Are there questions in the audience? Patryk, yes, I can see you.
Hey, Leah, thanks for presenting this. This is so cool to have like a big overview about all the methods, and especially the microstructural measurements or validation approaches. That's really, really cool. I was just wondering about figure 7, where you showed the SNR maps. There seemed to be like a systematic pattern there, right? Showing an almost gradient-like pattern that goes from medial to anterior and posterior. What's the reason behind this? Like, is it the acquisition direction, or why do these SNR maps look like they look?
So usually, like in so parallel imaging, so when you have a phase array coil, your signal is higher, like in the surface, because you are acquiring from outside the brain. So of course, like in proximity of your acquisition, the signal is higher. And then when you go inside, you have this drop of signal. They call also like egg shapes. So you have like this hole in the middle. And this is also the reason why I experienced like in spectroscopy, when you are doing like spectroscopy here in the basic ganglia, your signal as a drop is not good, because yes, it's a limit in phase array coils that you have this homogeneity in acquisitions, so higher signal in the periphery of the brain, and then a drop inside, because yes, you're trying to merge all these different arrays, and then when you go in the middle, you have this most uncertainty. So I think this is why for that also, like when I used like a coil, they distribute, like it was a 64 channel arrays, and like in the posterior part you had more arrays, so sometimes you can have also this difference from here. It seems the contrary, but sometimes you can also have a difference like from in the anterior part and the posterior. It really depends on the geometry of your coils, and I think this is the reason why of these maps.
Okay, cool, thanks.
Welcome.
That's the answer you get when you ask a physicist.
I try.
That was perfect, perfect. Any other questions about this paper?
Can I?
Of course, Evie.
Yeah. So thanks, Leah. So it's really, it's really interesting to see this kind of paper, which make a good review of all the DTI techniques, diffusion techniques. So, and I'm always wondering where we are now in terms of diffusion literature. What do you think about this paper? Is it a paper about reviewing where we are now, and what do we have a maturity of this field? So this paper give you this this feeling, or is there still a long way to go?
Yeah, the problem is that I think that yes, we have a long way to go, because I don't know, sometimes I feel that we need like a consensus paper on diffusion measures, because of course here they are showing you that there are like plenty of models. Some of them are really cool, really interesting, and but yes, the question is always how we translate these to the clinics. Sometimes you really want to go simple, because these methods are really like complex to understand, also for a person that has like the correct background to understand that. But you need also experience, you need validations, you need like so also they talk like at the end, but I didn't really have time to read it, but about the harmonization, because then you put all together these measures like in multi-centers studies, and this is the way to go if you want to have a large number of data. And I think that the problem is, I don't know, maybe if we try to study and experiment for example, the diffusion sequences, you can find some interesting measures related to the microstructure. So it depends how you want to, the direction that you want to go to your study. So if you want to discover something that is new, so no one has seen like a specific in vivo measure of microstructure, and then you have to experiment and play different models at different acquisitions. Or if you want to give a clinic tool that everyone can use, so not related to the coil, the scan, and so like an harmonization of these measures. It depends. So I think that now we are going to both directions. So this is why you have this, I think, difference. Like in clinical applications and the state of art of diffusion imaging, because these are two different directions. I understand both. So I think maybe we are in a good point in the direction where you want to experiment new sequences, because you can really like you have really like this knowledge, so all these models, but maybe in the direction of the harmonization of these measures, we are not really at a good point. Maybe there could be an answer. I don't know. What do you think?
Yeah, I think this is the correct answer. And okay. I don't know if the future of the diffusion is. So you mentioned it. It was about the deep learning. Do you think it's the right way to go? Is there a solution using deep learning for all these techniques, and to find, like you said, harmonization between and find a common grounds?
So like, yeah, in deep learning sometimes seems like magic. You have this data-driven approach that really explain like the for example here the multi-compartmental models. But then of course you need like this training set that and then you have to be like uniform like in the acquisitions to apply these models that you have developed in other acquisitions. And I don't know, I need that there. I think that there in deep learning the like expertise needed to like jump a little bit higher. So you also in like managing the computer, the hardware, so you maybe for deep learning, I think you need like some like in the team where you're working with diffusion MRI, you need like some people that are really specialized in that. So maybe for deep learning is that you need like maybe a new figure in the team for doing that, but there are people that are studying this field. So I think it's a promising field, but it's like a few people are doing that, so it's not so widespread, maybe.
Okay, thanks.
You're welcome.
Thank you both for that discussion. I just threw in a picture as a background that Etta housed it a couple of years ago using deep learning algorithm on tractography, just for your information. Now, with that, we're at the end of our time for today. Thank you so much for joining us, especially for those who are supposed to be on holidays today. We hope you have an exciting week in science, and we see you again next week for another round of Neuroccino. Have a lovely week. Bye.
Bye.
Thank you. Bye.
Bye.